Thank you. Good evening, everyone. And today, uh, yeah, and today I'll be talking about dynamic fracture, emphasizing dynamic effects and counterposing the static and dynamic ways of thinking. It would be rather philosophical talk, and uh, I just would take an advantage of the previous talk by Dr. Zhao, who taught us about irreversible deformations, and so I will skip this part and mainly would concentrate on the fracture dynamics, and uh, so I just would probably skip this motivation part. This is obvious that it is very important to know some dynamic characteristics and dynamic parameters of the fracture process, just to prevent this kind of events and for safety and so on. But we use materials in dynamic conditions and all the time. In aerospace, defense, microelectronics, but surprisingly, I must say that we still don't have proper engineering standards for dynamics. And why? It's because the material parameters measured under the slow loading in static become dramatically unstable and unreliable under dynamic conditions. And so this is a roadmap of my talk. The main idea is that dynamics is a very special field. It revolutionizes our thinking. I will explain why classical approaches don't work for fast cracks and introduce a time-based fracture model. One that captures instabilities we see in many of the experiments. But I'm going to emphasize the main question. Do we actually think dynamically? It seems that by default, we think quasi-statically, looking for equilibrium even in dynamic situations. And it prevents us from understanding some of the principal features of dynamics. And I just want to start with very simple, even the primitive example of the problem of tension of the rod that I make out with my students, just to demonstrate this thing. I mentioned that I stretched the rod in statics and in dynamics, and I'm interested in the internal energy of the rod. The internal energy of the rod in quasi-statics is P squared, where P is just a force, a stretching force. And the static task is boring, very boring, but dynamic looks much more fun. We have to solve the wave equation with boundary conditions, and then I'm interested in this energy, internal energy. This is an integral over the rod. It consists of two parts. This is a kinetic energy, and this is an energy of deformation. And so I will just calculate this integral. And the result is over there. And so we have an internal energy of a dynamically loaded rod, which looks kind of paradoxically. So the energy disappears periodically. So imagine that I have a rod, I just applied tension, and I keep these forces to be constant. and the internal energy periodically disappears. And the question arises, where does the energy come to? Yeah, it looks like a paradox, but actually, it's everything is okay with the energy. Just remember that we have a force potential. We have a force potential, and the total energy of the system must include the force potential here. And being included in the Lagrangian, we will have a Hamiltonian principle, which would give us our problem. And so there is an energy exchange. Mathematically, this is a force potential, but engineers would say that there is a loading machine. And the whole system is a road with plus loading machine. And this is an energy exchange between our road and energy machine. And it comes to this effect, so that it seems that the energy disappears periodically, but it is just an energy exchange. Our road is like a kind of breathing. It takes an energy from the machine and gives it back. This is dynamics, as opposed, this is the simplest problem of road tension that demonstrates the principal difference of statics and dynamics here, even in these equilibrium conditions. And it is well known in practical engineering. Engineering practice knows this, and it works in the industry. Optimal characteristics of periodic impact are possible, yeah, and it's used in the crushing and processing of mining materials. Industrial engineers knows that well that an average lumpiness of crushed rock or the average size of rock pieces is very important for the frequency and impact duration control. So it is utilized, okay? And this is turns to be very fundamental important when conducting dynamic tests on materials for crack resistance. The removing load before the moment of fracture allows you to know the energy of the samples and the characteristics of crack propagation in extreme dynamic situations. This is a magnetopulse generator we have when we just utilize this system to produce explosive like loading, controlled loading in the plate. In this case, these are just this scheme. This is a plate with the crack, and we can produce magnetic field here, which gives us the controllable pressure of the level of the chemical explosion. And so in this case, we have a fracture event just at the moment when our sample doesn't interact with any support. And so we can know all the energy spared in the sample. And so it allows us just to evaluate the so-called Griffiths constant in dynamics. And we did it, and this Griffiths specific energy constant in dynamics and microsecond duration turns out to be 20 times, 30 times bigger than same characteristic in quasi-statics. And so this is a very close linked problem. This is the simplest primitive problem of the road tension and this technology, experimental technology. They based on the Ekman principle. Okay, yeah, and as for the fracture mechanics and crack propagation, this is just a classical approach. The classical approach, and we have Griffiths traditionally crack growth described using stress intensity factors, and particularly Irwin's criterion coming from the Griffiths energy flux idea is utilized. The thinking for dynamic is that once you know the material, there is a unique relationship between the crack velocity and the stress intensity factor or the energy flux needed to sustain the crack propagation. And so this relation, KV relation between K1 and velocity is supposed to be the material function. It directly follows from the energy balance, Griffith's energy balance applied to the dynamically loaded crack and moving crack. And so, and same in terms of stress intensity factor, we have to tell about the right parts of these critical conditions when we have a dependence, strain rate dependence, loading rate, local loading rate dependence, or dependence on the velocity of the crack propagation. And this also is interpreted as a material property. It's just equivalent approach. But is that actually a material property? Experiments suggest it may not be so simple. Yeah. So from this classical approach follows that it predicts the maximum speed that crack may attain as the Rayleigh surface wave speed, and it indicates that there is a unique relation between energy flux or crack drying forces characterized in terms of dynamic intensity, stress intensity factors, and the crack speed. So that the unique material curve is required. That is considered to be taken from some experiments. And the classic model and the majority of its modification include the dependencies of the considered material functions as the right part of this previously written equations. So, and how it is confirmed by experiments. Yeah. And this is a result of our extrapolation of our quasi-static thinking to dynamics. It is only partly confirmed by experiments. And I would say that even that nothing of that is definitely confirmed by experiments. And so this is how it does look like an experimental field. So let's look more closely on that. This is a classification of some experiments on this field. I took only classic measurements, and this classification is very conditional and approximate, but it reflects our situation well. And in some experiments, like Daly's and the Smith experiments, very classic experiments, we see the smooth and consistent KV curves like this one. KV curves, it's a KV relation. And others, like Kazarinov experiments, show the major differences between depending on the sample geometry. And so he just used the different geometry of the samples and established that this is kind of the KV dependency, but it is not a material curve. It depends on the geometry. And there's another group of experiments. The first group of experiments, they are associated with the slow loading when we accelerate the crack from zero to some essential velocities. But there is another group of experiments with when we have an impact loading, such like a Ravichandar and Knaus, very famous classic work. And the KV relation doesn't even exist in these experiments. There are just straight lines like this. So the velocity is constant, and the energy flux dramatically changes several times. And so it's this curve is just shifted here, just to compare what we see on the left and on the right. Yeah. And so in the third case, we would say that there is no dependency between KV and V at all. And so just to, looks very contradictory. And just to make out with this way, developing a new approach over the years, but around a different idea, the characteristic time. We have a dynamics, and we have a very essential thing that it's a time scale should be involved, not only as a parameter, not only as an additional dimension. And we just talking about the characteristic time, and this is a incubation-based approach based on the characteristic times, which was realized in different fields for spot fracture, for Gregg-Krauss association, for dynamic yielding, as Dr. Zhao Shisan told before, cavitation fluids, electrical breakdown, and dynamic melting. But I will just talk about only crack propagation now. And this is an example of how it works. In the case of quasi-brittle cracks, we have this critical condition, and it's a new parameter. It's called incubation time here. It defines the duration over which the stress must act to actually cause fracture. The KID is not just about force, but it's about how long that force acts. The incubation time criterion is essential non-local in space and time, and we consider the minimal fracture event, a minimal crack jump in our case, on the given scale level. And this way, the fracture scale level and spatio-temporal representative volume should be introduced, like this one, in space and time. And we have two linear size, that is linear size in space. This is a fracture linear size, and the corresponding size in time scale. And so this is an approach. And how it works, imagine that we have a semi-infinite crack here. And we have a pressure of this crack. And then we have a pressure of this kind, it's like a rectangular pulse, or trapezoidal pulse, that acts up to the moment of fracture. And this is a stress intensity factor growing up to the moment of fracture. And now I just take this moment of fracture as a duration and just stop loading. And then I conduct the second experiment with this duration. And I will just decrease a little bit this amplitude. What happens if we still will have the fracture? It turns out that, yes, we will still have the fracture. This is a new position of my amplitude. But the fracture will be on the decreasing stage of the stress intensity factor. And so this way we can come to the threshold loading. So the lower loads will not produce the fracture. But in this case, this is observed experimentally. This is experimental procedure that would allowed us to get it. So when we conducted experiment by pulse magnetic field and started to investigate the microsecond durations of the pulses and found the threshold amplitudes, we got the fracture delay in PMA8, so that the crack stress intensity dropped 5 times before the crack started to propagate here. It was first predicted and calculated by Shock and Kazarinov in these classical works. But that it was a tiny fracture delay, but we could measure this big one. Yeah. And so actually, we have two cases when the load acts up to the moment of fracture. Yeah, and this is a upper curve of this yellow region for K1D. And then we have another case, the threshold loading, where this one, the lower boundary of this yellow region. So when we have essential fracture delay. And so this is a region of the possible value of the fracture dynamic stress intensity factor at the moment of initiation of K1D. It's just for one material we have the set of possible values of K1D here. And so and the calculation doesn't need material curves. It's based only on material constants. The two constants are needed here, K1C and the incubation time, to get this phenomenon. Yeah. And now, just I want to. This is just an example how it is realized for particular materials. And now I want to just to apply it to crack propagation. And I want to consider to crack propagation, and so it can be easily incorporated in the finite element technique and with the special node release technique. And so this is a criterion that can be just incorporated in any scheme, finite element scheme, and we are still in the frameworks of linear elasticity and linear fracture mechanics. Yeah. And so I just want to check two possibilities: the slow loading with the slow growth of the stress intensity, like this green line, and the fast loading with this green line. In this case, we have a small scatter between lower boundary and upper boundary of these yellow regions of possible stress intensity factor. And in this case, we have a big one. Yeah. And now I want just to consider two schemes, the quasi-static schemes, which was conducted by Professor Kartkov. Is based on the double cantilever beam specimen and the single edge node specimen. When we accelerate crack up to the certain values of the crack velocity from quasi-statics, and another scheme like Ravichandar and Knaus realized so that we have a big plate loaded by the impact, very intensive impact here. And so there are just results for the first results for the impact. So it is just, again, how it can be calculated and incorporated into numerical scheme. And the first result just from impact. And we have this straight line. In the case of very intensive impact, we have this straight line. And so this the KV dependency provided by the energy balance doesn't work in this case. You have some constant velocities and the big scatter of the possible value of K critical stress intensity factor accompanying the moving crack here. So like this one. And in the case of and so it looks like what we saw in the experiments by Ravichandar. And so, and this is another case when we have a double cantilever and single edge notch beam, and there are look like we have a KV relation, but fitting is applied to get these curves. What is fitting? Fitting means that when we have a slow loading, actually we observe the scatter in stress intensity factor, but it is in very small ranges, so that actually we can approximate it by the smooth dependency between K and D here. But that says if the loading is slow, we can draw a smooth KV curve. That's close to what Griffith's theory predicts. And it works reasonably well under gentle, slow loadings. And yes, our result match experiments, at least qualitatively, explain the KV paradox. Yeah. And so this is a conclusion. The model contains a minimal set of material constants and does not contain material functions at all. Of course, this is far from taking into account all the features of different materials. This is a phenomenology where macrostructural features of the material influence the basic material parameters of the model, but it is approximately right. So thank you for this.